This is integration using the substitution method. This method is used when we cannot use the simple integration rules, thus calling it the substitution method. Alright, this method is to find an integral. It has to be set up in a certain way. This is also known as U substitution or the reverse chain rule. Kind of reminder, when we use chain rule for derivatives, we needed to have a composition function. That way we could have applied the chain rule. Alright, this premise of integration by substitution, kind of the same way. We want to see if there's a function inside a function that we can apply this reverse chain rule. Kind of what I mean by that is the chain within the function is by very similar to the Russian nesting dolls. Is there a function inside another one, kind of like a doll inside another doll. For my method, we are using 7 steps. Others may use less steps. I like using these 7 because it will always work in most cases, 90-something% of the time. In later examples, I'll show you quote-unquote a shortcuts, this is when others, or why others use less amount of steps than my 7. First thing is we are letting the variable u equal the inside function. This is why this is called u substitution. Second step, we're going to take the derivative of u with respect to x. What that means is that we are going to use implicit differentiation to get a du and a dx. Third step, we're going to solve for dx. Step number 4, this is where the method gets its name. We're going to substitute in the original, we're going to substitute u and dx in there. From there, we're going to simplify that new integration that we got. Then we're going to integrate XSS in step 6. Once we finish step 6, we're going to be given an integral or an anti-differentiable function in terms of u. Because this original function was in terms of x, this is where step 7 comes in place, where we're going to substitute back in place for x. Alright, here is example 1. We are going to evaluate the integral of the square root of 5x minus 4 with respect to x or dx. Alright, first thing we want to do is u be the inside function. So this part is going to be side work. Right, I like using my side work over here, and then my main work kind of follows over here. Others like doing it the other way around. Side work in this end, the work follows it this way. Me personally, because side work ends here, I have a lot more space to work down here of how I set it up right here. So my inside function is, and I'm going to highlight it here with a color, right, yellow, is 5x minus 4. Everything inside. So that's what I'm going to let u equal to. U equals 5x minus 4. That's our first step. Second step, I need to find du. In order to find du, I need to take the derivative of this equation. Du equals the derivative of 5x minus 4 with respect again to x is just 5, and then dx. Again, implicit differentiation. Step 3, solve for dx. In this case, I need to divide both sides by 5. I think that looks better. So we have dx equals du over 5. Here is our side work, and then now here is where our main work is going to begin. Step 4. So we're going to substitute for u. So I'm going to replace the 5x minus 4 with u and the dx. This dx is going to get replaced with the du over 5. So this is going to change the way how it looks. So we're going to have the integral of the square root of u. The dx, it's now du over 5. Again, that's being multiplied. So now, since we have over 5, same thing as 1 over 5, that is our constant, we can remove that, not remove it, I'm sorry, we can put that on the outside, so it becomes 1 over 5 times the integral of u to the 1/2 du. Alright, this is me simplifying. Now I'm going to integrate. Since this is 1/2, I need to add 1, so take my constant times u to the 1 over 2 plus 1 all over 1/2 plus, in this case I'm kind of jumping up ahead, but 1 is the same thing as 2 over 2. Last but not least, don't forget plus constant. Alright, we're going to simplify this out. 1/2 plus 2 over 2 is the same thing as 3 over 2. 3 over 2 plus c. Because we have a fraction inside of a fraction, this lower denominator becomes all the way to the numerator. So this is going to be 2 times u to the 3 over 2 all over 5 times 3 is 15 plus a constant. Now we want to substitute back in x. Alright, so that means that this u is going to get replaced again with 5x minus 4. So ultimately this is going to become 2 times 5x minus 4 to the power of 3 over 2 all over 15 plus our constant. And again, this is 2. And this is the final answer for example 1. Here we have example 2. We're going to evaluate the integral of the binomial 3x cubed minus 5, which is raised to the 5th power, times 9x squared dx. Again, the premise begins very same. We're going to let u equal this inside function. In this case, u, or I should say the inside function, is 3x cubed minus 5. Alright, that's first step. Second step, find the u, meaning take the derivative to both sides. The root of 3x cubed minus 5 is 9x squared dx. Alright, and then this is what I mean where a lot of others don't require these two parts here in terms of solve for x. Alright, because I am going to replace the dx with the u and some other else, right? In here, I already have a 9x squared dx to replace it for du. In my original problem, it's already there. In most cases, this is not going to happen, and this is why sometimes I don't like using these shortcuts. I like using these 7 steps. Alright, so this is going to become the integral of u to the 5th power. Alright, this 9x squared dx is the same thing as du, so we're going to have du right here. This is already simplified as much basic as we can be. Now we are going to integrate. So we have u to the power of 6 over 6 plus our constant. Now we're going to substitute back in x. So we need to put in, instead of having u, we need to replace it with the 3x cubed minus, this is wrong. Let me find my eraser here. This is going to be 3x cubed minus 5, and that's raised to the 6th power over 6 plus our constant. Text, here's the triangle, I'm sorry, our square, and there is our box in for a final answer. Here we have example 3. This is 10x times the cube root of 5x squared minus 3 dx. Again, we want the inside function, So that's u equals 5x squared minus 3. If I find the derivative, du equals 10x. This one's a little bit harder to see. Alright, and I'm forgetting my dx. If I solve for dx, dx equals du over 10x. And this is the reason why I like saying to solve for dx. From here, when I substitute u and dx into this original here, I have the integral of 10x times the cube root of u times dx now gets replaced with du over 10x. And this is the reason why I like solving for dx, because this 10x and 10x will reduce each other to 1. Alright, now I have 1 times the cube root of u du over 1, which is which is the integral of u to the 1/3 du. So from here, I'm just going to integrate, add 1, u to the 4/3 over 4/3 plus our constant. Again, a reminder, when we integrate, we no longer have our integral sign. Right, if I have a fraction within a fraction, the super denominator, the very bottom denominator, is going to go over to the numerator. So this is going to end up being at 3u to the power of 4 over 3 all over 4 plus our constant. Step 7, replace in the x over here. So that means that we're going to have styled differently now. 3/4 times 5x squared minus 3 should be squared to the 4/3 plus c. And that there is our final answer. Get that in black, that would look a bit more aesthetically pleasing. Again, this is wrong shape. That's supposed to be a square. And not a cube. Example 4. Now I got rid of this. See if you can actually remember. First thing you want to do, again, let u equal the inside function 2x to the 4 minus 3. Take the derivative to both sides. And that is going to equal to 8x cubed dx. Again, this is going to serve as a perfect example of why I like solving for dx. Dx equals du over 8x cubed. From here, substitute in our values. We have 16x cubed over 2x to the 4th minus 3 gets replaced with u to the power of 5. Dx gets replaced with du over 8x cubed. Alright. Here, the 8x cubed, the x cubed reduce each other out, or reduce out to 1. 16 and 8, 2 over 1 respectively. So now we end up having the integral of 2 over u to the power of 5 du. Since 2 is a constant, right, I can pull this out. I am simplifying or making this a bit easier to see. I really hate things how this is not as sensitive as my other one is. Alright, from here we integrate 2 times u to the power of negative 5 plus 1 over negative 5 plus 1, adding a constant. Here we have 2 to the power of negative 4 over negative 4 plus our constant. Mr. Shouldn't it be a 2c here when I'm distributed 2 with the c? Yes, you are correct. You are correct, but in this case, this here, it's still, I don't care what that constant is, because when I take the derivative of this, it's going to give us this original integrand of what's in here. So now to simplify stuff out, 2 and 4 reduce. So now that becomes negative 1/2 u to the power of negative 4 plus a constant. Now we're going to do it all back in together. So we have negative 1 all over 2 times 2x to the 4th power minus 3 plus the constant. That there is the final answer. Alright, I know it's harder work to take integration, but because these are indefinite integrals, I don't want you to be just like this means. You finish integrating the problem, but you don't get the full credit because you forgot to put the plus c adding your constants. Please, don't be like him. Alright, that was the sort of kind of easy part. Let's move on to a little bit more challenging stuff. Alright, we're going to deal with integration with some trig identities. I kind of want to remind you that the integral, or say indefinite integral of cosine of x with respect to x is equal to sine of x plus a constant. Or the other way of saying it is the antiderivative of sine of x with respect to x is equal to the negative cosine of x plus any constants, any number. Alright, hopefully this kind of review, it'll setting us up for our next example. Here we have example 5. We are evaluating the integral of negative 16x cubed times cosine of 4x squared minus 5 dx. Alright, again, the inside portion is this inside here, so this is what we're going to let u equal to. U equals 4x to the 4th power minus 5. Alright, if you see the pattern, usually the u is the one with the function that has the highest exponents. Alright, if I take the derivative, du is going to equal to 16x cubed dx. Here it sets up nicely. I already have a 16x cubed and a dx. Right, I'm going to set this up the other way by solving for dx. That way you can kind of see stuff that it will always work out. Alright, from here, right, we are going to take the indefinite integral of negative 16x cubed times the cosine of, now in this case, is u. Dx is now du over 16x cubed. Alright, from here, 16x cubed reduces, 16x cubed reduces. I better be careful that I not forget about this negative here. So now what I'm going to do, since this is negative 1, I'm going to bring it outside. Take the integral of the cosine of u du. As we saw in the previous slide, the integral of regular cosine is regular sine. So that means that this is going to be negative. This is negative. Cosine is sine of u plus our constant. Again, replace back the x in for the u. We get negative sine of 4x to the fourth power minus 5 plus our constant. And that there is the final answer. Alright, some more advanced trigonometric integration review. The integral of the secant squared of x dx is equal to the tangent of x plus c. I just won't read them. I'll give you a couple of seconds for you to look at, then I'll move on. Alright, I'm going to move on. If you need more time, you can come back to it, or you can just simply press pause. Alright, this is the last example that I have for you for this set of notes. We're going to integrate this function here, the integral of 2 times tangent to the fourth power of 2x times the secant square of 2x, all with respect to x. In this case, you can kind of double up in here if you want to. If you don't double up, that's fine. What's going to end up happening is you're going to end up using substitution a total of 2 different times, and then you have to kind of go backwards 2 different times, and I'll show you both ways in that sense. Okay, I'll tell you the first way in terms of the inside function. If I let u equal 2x, then du is going to equal to dx. Right, so that means that dx equals du over 2. Alright, so from here I have the integral of 2 times the tangent to the fourth power of u times the secant square of 2x, no longer 2x, this should be u du over 2. What this happens, the 2's reduce to 1, and I no longer have the other, I guess you can see, weird or nasty integrals, right? So this becomes the integral of the tangent to the fourth power of u times the secant squared of u du. Alright, so I did mention that this is going to become a second time. Right, from here we're going to let v equal to, in this case, tangent of u. So if I take the derivative, again, because it's the one with the highest power, right, the derivative of a tangent is the secant square of u, in this case du. Since the u is here, I need to solve for the u. The u equals dv over the secant square of u. Don't forget my little parentheses in here. Alright, so now hopefully this color coding kind of helps out in terms to distinguish which one is which. Right, so now I have the integral of, now it's v to the fourth power times this now gets substituted, right? So I'm going to keep that there for now. Secant square of u. This du gets replaced with this here. dv over secant square of u. See what I mean by when we solve for the dx or the other one, in this case the u, secant of u and secant square of u, I should say, reduce each other to 1. So now this is going to simplify as the integral of v to the fourth power dv. Alright, so now that we're here, now we're going to integrate. This becomes v to the fifth power over 5 plus our constant, right? I need to replace the v with what I originally had, so now this becomes tangent to the fifth power of u over 5. Because originally it was with x, here we have with u, I need to not move back, but I need to replace the u with the 2x, and now I have tangent to the fifth power of 2x all over 5. Alright, and that there would be our wrong answer. Why is it the wrong answer? I missed something that I dropped on my way over here. What did I forgot? I forgot to keep adding our constant. So let me extend this final answer. And actually this here is now the final answer, ladies and gentlemen. Alright, please don't forget that C. It is very important in this sense. Please don't make me go into worst case scenario and do this, giving you 4 points for doing all the correct work, and then subtract you 5 for getting your plus C. So don't be like that other mean that you forget your plus C that you make me turn into him. Alright, that's it for now. In a bit, I will be posting up the other part in terms of what I told you, in terms of the double 2 steps in one. Alright, again, every time you waste browsing means, like I usually sometimes do, you can be solving integral equations. Alright, I told you I was going to do the other way, the 2 steps in one type of thing. Alright, in the second step, when I finish, we let v equal to the tangent of u. That's going to be the big case. I'm going to put 2 steps together. I'm going to let u, the new u, be the old u and the old v. So what I mean by that is u is going to equal to tangent of 2x. When I do this, the derivative equals, the derivative of tangent is secant squared of 2x times 2 dx. Here I actually used the chain rule, right? And now I'm going to solve for dx, which is going to be du over 2 secant square of 2x. And now I can actually start substituting integral of 2. No more tangent. I'm just going to go straight into u to the 4th power. Alright. Times the secant square of 2x. No more dx. I'm going to have du over 2 secant square of 2x. Alright, from here the secant squares of 2x reduce each other out to 1. This 2 and this other 2 reduce each other out. And I end up with the integral of u to the 4th power du. So, kind of ends up being at the very end of what the other one had. I won't finish this up because it ends up being at the last part there. The last part, by that I mean it ends up being at the other step that we previously had. And if I go a couple slides, right, it ends up being right here, just that instead of v, now it's a u over here, right? Alrighty then, that's it. Now it's time to go. Now it's time to start practicing, right? Because you don't want to bounce at means.